So in this video, we're going to be covering topic 9.3, maxima and minima, first and second derivatives, which is the relationship between a function and its derivative. We'll start with example 9.7, and it says, using differentiation, find the coordinates of the vertex of the parabola with the equation y equals x squared minus 8x plus 14. So we have to find the derivative of this. And we know it's going to be 2x minus 8. So all you have to do is equal this to 0, and that's where you're going to find the maxima or the minima. Or at least you can find something called the critical points. So if we solve for x, we're going to get 2x equals 8, and then x equals 4. So that means that for this parabola, at x equals 4, you have a vertex. Graphically speaking, if this is the vertex, the slope of the line, of the tangent line, is 0 there. But we still have to plug in the 4 in the original function to find the y coordinate. So y would equal 4 squared minus 8 times 4 plus 14, and this is equal to negative 2. Therefore, the coordinates of the parabola are 4, negative 2. So now we're going to go and work with example 9.9, and it says, for the function f of x equals x to the 4 minus 2x cubed, find the coordinates of all stationary points and describe them completely. So stationary points are points where a graph has a slope equal to 0. So those stationary points can be maximum, minimum, or points of inflection, as we will see in this example. So first thing we have to do is find the derivative. So let's do the derivative of f of x. And we know that this will be 4x cubed minus 6x squared. So in order to find the stationary points, again, we have to equal this to 0. Now notice that here we will have to factor, right? We can factor out 2x squared, and then we're going to get 2x minus 3. This equals to 0. So what are the solutions? The solutions would be x equals 0 and x equals 3/2. So those are the stationary points. Now what we have to find out is if they are points of inflection, maximum or minimum. For that, we can use a sign chart. So we can draw a line like this and then just put 0 here and put 3/2. And because they don't talk about a domain, it means the domain is all real numbers. So we have to consider positive infinity and negative infinity. Okay, so what we need to do then is plug in values before 0 in the derivative. So we can use this here and plug in, let's say, negative 1. So what would we get if we plug in negative 1? If you plug in negative 1, you're going to get a negative value. That means that the graph is decreasing at that point, right? If you can try it out with a value like negative 1, and you will see that the derivative will give you a negative value. Therefore, it means that the slope is negative or the graph is going down. So let's see what happens between 0 and 3/2. So we could test a value like 1. If you plug in 1, you're going to get a negative value again. That means that this here is a point of inflection, and it's not a maximum or a minimum. How do I know that? Well, because the graph is still going down. And then at 0, it probably has a point of inflection. We will see it in the graph in a bit. But what happens after 3/2? After 3/2, if we plug in something, say like 2, we're going to get a positive value. You can test that for yourselves. So if this is positive, it means that the graph is going up after 3/2. So that means that this is a minimum right here. 3/2 is a minimum. Why? How do I know that? Well, because if this is negative, that means that the slope of the graph is going down, and then it reaches a minimum, and then it goes back up. So this is definitely a minimum. We're going to see that in the next slide, where we actually have the graph. So in this slide, we can see the graph. Notice that we have the stationary points at x equals 0 right here. You can see that the slope, if you draw a tangent line, is going to be 0, just like here at the minimum. Now notice that the graph itself is going down, 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 is going down. That's why we had negatives when we plugged in values before zero. We got negatives, meaning the slope is negative. And after zero, but before 3/2, we also got a negative value, which is reflected here by the slope of the graph. Then we reached the minimum, like we said, at 3/2, and then the slope became positive, which confirmed that this was a minimum. Now, what is a point of inflection? A point of inflection is a point where the graph of a function changes its concavity. So notice that here, before zero, the concavity is upward, and after zero, the concavity is downward. That's something that we can do with something called a second derivative test, and we will see that shortly. Very well, so now let's focus on example 9.12, and this is a physics problem with velocity, position or displacement, and acceleration. One of the most common applications of calculus is precisely these problems of position, displacement, velocity, and acceleration. In fact, it is said that Newton developed calculus in order to solve this type of problem. So it says an object moves along a straight line so that after t seconds, its displacement from its origin is s meters. Given that s of t is equal to this minus 2t cubed plus 6t squared, find letter A, expressions for velocity and acceleration at time t seconds. So let's do part A first, and then we'll focus on B and C. So number one, how do we find velocity? So velocity is simply the derivative of displacement. So if we find the derivative of displacement, that is really going to be the velocity in terms of time. So this is going to be minus 6t squared plus 12t. So this is now a function that will give us the velocity of the particle at time t. Then for part two, they want the acceleration. The acceleration is the second derivative of displacement or the first derivative of velocity. So that means that the acceleration we can find with minus 12t plus 12 as a function of acceleration. Now you can think of this in terms of slopes, right? If you have a graph of the displacement, the slope is velocity. If you have the graph, excuse me, if you have the graph of velocity, its slope will be the acceleration of the particle. So in part B, they want us to find the initial velocity and the initial acceleration. Now that's pretty simple because all we have to do is plug in time zero, right? So when time is zero, what's the velocity? So that would just be zero, right? If we plug it in, minus 6 times 0 squared plus 12 times 0 will give us 0. Therefore, 0 meters per second. Now don't forget to use units. Sometimes they write them like this as well, right? Meters per second. So that would be part one, right? The initial velocity. Now part two, the initial acceleration, the same thing. And that's going to be acceleration when time is zero. So this is going to equal minus 12 times 0 plus 12, and this equals 12. Therefore, at time equals 0, the acceleration was 12 meters per second squared. Okay, now we go with part C, and this is a little bit more complicated, but it's not that hard. But you just need to pay attention to this for a second here. So let me erase this, and we can focus on part C. So in C, they want us to find the maximum displacement, and they want us to find the maximum velocity. Okay, so to find the maximum displacement, we need the derivative of displacement. And the derivative of displacement, we said already, is velocity. So if we grab that velocity function, so we know that velocity is equal to minus 6t squared plus 12t. So what we have to do is like we were doing before, when we want to find a maximum of something, we equal it to 0. We equal the derivative to 0 because at the maximum points, the slope of the graph of displacement is equal to 0. So that's where the velocity is 0. So we solve for this, same procedure. Let's just factor minus 6t, and this is going to be equal to t minus 2, and equal this to 0. So notice that the solutions to this equation are t equals 0 and t equals 2. So what we have to find out is whether these are maximums or minimums. Now, one thing we have to take into account is that this graph or this problem wants to know about maximum velocity and displacement in this time interval here, so from 0 to 3. So we do the same thing we did before. We do a sign chart. So let's start with 0 and then 2, and then we have to test values like 3. Okay, so just here and here. So notice what happens if we plug in a value between 0 and 2, such as 1. If you plug in 1 in this function, what are we going to get? We're going to get a positive value, right? You can test that for yourselves. You're going to get something positive. If you know that if you plug in 2, you're going to get 0, of course. But what if you plug in something between 2 and 3, like 2.5? You're going to see that you get a negative number. So what does that tell you? That tells you that the graph for displacement is going up here. It reaches a maximum, and then it starts going down. So that means that the maximum displacement will occur at t equals 2 seconds. So we have to plug in 2 into the displacement function. So s of 2 is going to equal negative 2 times 2 cubed plus 6 times 2 squared. And if you do that, this is going to give you 8. So that means that at t equals 2, the particle reached its maximum displacement of 8 meters. And that would be the answer for that first part. So how about the second part, where they want us to find the maximum velocity? Well, we would do the same thing, except that now we won't use the velocity function, but we will use the acceleration function. So let me erase all this, and let's do that for the acceleration. So we say part C, part 2 of that, maximum velocity. So again, we need the acceleration. And we found before that the acceleration of t is the second derivative of the displacement or the first derivative of the velocity. And we found that this is equal to minus 12t plus 12. So again, what we do is that we equal this to 0. And this only has one solution, right? Where t equals 1. We still don't know if this is a maximum or a minimum. So we have to use the table again. So remember that because the time interval is from 0 to 3, we have to test those values. So 0, 1, and 3. So what happens between 0 and 1? Let's say if we put a value like 0.5, notice that if you put 0.5 here, this is going to be 6. So therefore positive. That means the graph is going up. Okay, so how about between 1 and 3? We can test 2 seconds, and 2 seconds is going to give us negative 12 for the acceleration. Therefore, here we have a negative. Therefore, the graph is going down after 1 second. That means that you have a maximum velocity at time equals 1. So time equals 1. At time equals 1, what is the velocity? So we have to plug in 1 into the velocity function, right? So this would be negative 6 times 1 squared plus 12 times 1, and this is equal to 6. So at time equals 1, the maximum velocity is 6 meters per second. Now, in this problem, we didn't have to worry about the values of the extremes, but sometimes you have to plug these in as well, just to be sure that you're not going to get a velocity higher at the endpoints of the interval. In this case, we don't have that problem because the graph is going up and then it goes down, so there's no way that 0 or 3 are going to be higher than 1, so to speak, right? And the same thing happened before. But in general, it's good to also plug in 3 and 0 just to see what the velocity would give you. Very well, so this is going to be the last example on this video, and it's example 9.13. And it says determine the intervals on which the graph of y equals x to the 4 minus 4x cubed is concave up or concave down, and identify any inflection points. So we have stationary points, which we can find with the first derivative, but the first derivative doesn't always catch all the inflection points. I'm going to do this differently from the textbook because I want you to see two things. I want you to see how we can find the minimum and one inflection point with the first derivative. So let's do the first derivative of y. So the first derivative of y is going to equal 4x cubed minus 12x squared. So we equal this to 0 again, just to see where the slope of this graph is 0. Let's factor out 4x squared, and we're going to get x minus 3, and we equal this to 0, and we see that the solutions for this equation are x equals 0 and x equals 3. So let's test those values, right? So let's test 0 here, 3, infinity, and negative infinity. Okay, so what happens if we plug in, say, -1? If we plug in -1, we're going to get a negative number here. You can verify that for yourselves. Okay, something between, we know that 0 will give a 0 because that's either a maximum, minimum, or an inflection point. Between 0 and 3, we can plug a value, say 2. And what are we going to get? We're going to get a negative again. So notice that because there's no change of sign, that means that this graph is going down, and then it has a little inflection point, but it's still going down after the 0. That's why we know it is an inflection point. So let's see what happens with 3. If this changes to positive after, like we can see it will, if you plug in 4, you're going to get a positive value from this. That means that the graph goes up. So notice that we found a minimum at x equals 3 and an inflection point at x equals 0. But the most direct way to find all inflection points is by using the second derivative test. So let's find the second derivative. And the second derivative is just doing the derivative of the first derivative, right? And if you do that, you're going to get 12x squared minus 24x and equal this to 0. And then we factor out, right? 12x. So it's going to be 12x times x minus 2. So notice that we found 0 again. So 0 is an inflection point. And so is 2. Now, what we're really testing with the second derivative is concavity. So where there's no concavity, you have an inflection point. That's why this equals 0. That means there's no concavity. So that means that 0 and 2 are inflection points. So let's do another table using 0 and 2. We already know that 3 is a minimum, so we won't bother with that. 0 and 2, and you know that positive infinity, negative infinity. Okay, so what happens if we plug in a negative value or anything lower than 0 into the second derivative? Let's say -2. This is going to be positive before 0. So if you get a positive value from the second derivative, that means the concavity is upward concavity. At 0, there's an inflection point, but what happens between 0 and 2? Say with 1. With x equals 1, you're going to get a negative. That means the concavity is downward. And then what happens if we plug in a value larger than 2? Let's say 3. We can plug in 3. Why not? Well, 3 is going to give us a positive value. That means that the concavity at 3, although it's a minimum, the concavity is upward. Okay, so we will see all this graphically in the next slide. Very well, so here we have the graph. And notice that we can see all the patterns that we found before. So with the first derivative, we found this x here, right, where x equals 3. The slope is 0, and we found that this was a minimum. Then we also found that at 0, 0, there is a stationary point as well, right? But this one is not a minimum or a maximum. You only have a change in concavity. Now, when we did the second derivative test, we found another point of inflection that we could not find the first time. And notice that this is right here is a point of inflection, as we will explain in a second. So notice that the graph is going down, right, from negative infinity to 3, which was a minimum, and then it went up after that. That we knew already. Then we did the concavity tests for values before 0, and we got positive. Notice that it's concave upwards. After 0, it's concave downwards. But then after 2, the concavity changes. So here, the concavity is downwards, but then after that, it changes to upwards as we tested with x equals 3.